Let's now take a look at some stochastic differential equation models that arise in physics and engineering. The first example is a problem studied by Einstein already in 1905. It's actually one of the first constructions of the Brownian motion in mathematical sense. In this setting, we think that we have a set of particles denoted here with red dots, which then have a probability of jumping to another place with the distribution of the lengths of the jump looking like this. So that distribution is in the derivation denoted as phi of delta. Then, as shown in the lecture notes, we can actually determine the next density of the particles if we know the previous density of the particles, just because we know this distribution. So it shows to be x t tau. So this is the density at place x at time t plus tau. This is equal to the integral of x plus delta, where delta is the jump length at time t, and then have the distribution, and we integrate over the deltas. And actually in the lecture notes it's written for the number of particles in very small time intervals, so you multiply that with dx. But now it turns out that if we think very short time intervals, we can kind of take the limit of tau going to 0 and delta going to 0 in certain sense. And what now happens is that you can show that this density will end up being the solution to this kind of something called diffusion equation, where the time derivative of u is equal to a constant times the second derivative of u with respect to the x. And now this was the key result in Einstein's paper, because you can actually show that this d is a macroscopic property of the system, but still you could express this d also in terms of the microscopic properties of the system. And one of the key results was the mean square displacement formula for very small particles as function of the certain chemical constants, number of particles, as well as basically the temperature of those particles. And finally, so what does this construction have to do with Brownian motion? Is that mathematically this kind of construction is actually a construction of the Brownian motion. And it turns out that the probability density of Brownian motion evolves according to that kind of diffusion equation that was actually derived in Einstein's paper. So it is a equation derived for a Brownian motion. The second example is a construction of Brownian motion by Langevin. It is a physical Brownian motion in the sense that it's not exactly the same thing as the Brownian motion in pure mathematical sense. So in that construction we have this kind of situation. So we have random collisions between particles in some liquid or fluid with the temperature, so that there's a random component acting on the particles. So we have a couple of forces acting there. Well, maybe we can first recall that the physics of the particles are governed by the Newton's laws in this range of velocities that we assume. So the force is equal to mass times acceleration is our equation. So we assume that mass is some m, we can even set it to unit mass, and the acceleration is just the second derivative of the particle's position. So all we need to determine is just the forces that act there. So the first force that we consider is the friction force caused by the liquid here. So in the model by Langevin, it's assumed that the friction model is proportional to the velocity, and it has the form of Stokes' law. So it's 6 pi, a constant, which is actually the viscosity of the liquid, times the radius of the particles, and then times the velocity. And of course the velocity is just the second derivative of the particle motion. Then, in addition to this first force, we have another component which is completely random component. This random force is, well, white kind of noise, and it's caused by random collisions between the particles. We assume that the collisions are rare enough so that we can think them as independent, so that's why it causes just the random directional impulses to the particles. And if we now write down the equation, we have that the ma, which is m times the second derivative of x with respect to the time, is equal to first force 6 pi constant r, the second derivative of x, plus our random force. And now we can actually notice that this is exactly a stochastic differential equation of second order that we are considering. So we could call this as gamma, for example, and we have been denoting this random process as Wt. And what Langevin showed is that also from this model, by putting certain assumptions of the square or the variance of the process, we can actually derive Einstein's result again by assuming that the correlation length is basically small enough. Let's now take a look at the RC circuit that's shown here. So we have a input voltage which is Wt, and the output voltage is Vt, and then we have a resistor and a capacitor in the system. We can actually write down the Laplace domain transfer function of the circuit quite easily for it. So it says that the output in Laplace domain is equal to the transfer function, which is 1 over 1 plus RCS, and then we need to multiply that with the Laplace transform of the input. If we now take the inverse Laplace transform, then we end up into the differential equation. So the time derivative of v is equal to minus 1 over RC v plus 1 over RC Wt. Well, this is a function of t as well. And now, if we put a white noise process inside here, what we have is actually a stochastic differential equation model. And so we can basically analyze the output of a RC or other circuit with white noise input by rewriting the stochastic differential equation form of it and then analyzing the properties of that. And this is actually just a Einstein-Uhlenbeck type of stochastic differential equation, which we can solve quite easily. It is also possible to analyze something called phase-locked loops using stochastic differential equation models of them. So for example, this particular model of phase-locked loop was studied by Witherby in his 1966 book. So in the case of sinusoidal input, we can actually write down the equation for this model as the time derivative of phi is equal to omega minus omega 0, but omega 0 is the frequency of the input. Then constant times k times sinusoidal of phi minus k times Wt. And now, if we wish to analyze the response of the phase lock loop to white noise, what we need to do is that we basically put a white noise as the input here. And now this equation is a stochastic differential equation which governs the basic properties of the phase lock loop. And you can even derive the Fokker-Planck equation, which gives the probability density of the stochastic process as function of the noise inside. So let's take a look at this quite simple model of a car. So we have two forces acting on the car. First is W1 and second one is W2. The assumption that we will now use in our model is that we assume that both of the forces are actually random processes, in particular white noise processes. And now if we assume that our mass of the car is actually unit mass, we can write down the differential equation for the coordinates x1 and x2 basically for the basic Newton's law. So the Newton's law says that the second derivative of first component is equal to noise in the first component, and the second derivative of the second component or coordinate is equal to the force acting on the second coordinate. But now this is a second order differential equation, but we can rewrite this as a first order differential equation. So what we do is that we simply say that we have another random variable or another state variable x3, which is equal to the time derivative of x1, and then fourth component which is equal to the time derivative of x2. And now we can rewrite this as the first derivative of x3 and this as the first derivative of x4. And now if we collect all the equations together, we can write this down as x1, x2, x3, x4 time derivative will be equal to, well, we will be clever and rewrite this in this kind of form. So we will have a matrix here which multiplies this vector x. So the time derivative of x1, well, it will be equal to x3. So 0, 0, collect x3 here, 0. The time derivative of x2 will be given by this equation, so it's equal to x4. So 0, 0, 0, collect 1 here. Or collect x4 here. And then the time derivative of x3, well, it's here. It doesn't depend on x, so actually we have zeros here, and for the same reason zeros here. But the white noises are on the right. So what we do is we plus and put a vector of white noises here. And then we need to figure out what kind of matrix we should put here. So we should have so that for the first and second components, we don't have any explicit white noise entering, but the white noise enters the derivatives of x3 and x4. So for the first two components, we have 0, and then we should have 1, 0, 0, 1 to get everything right. And now we can call this as f, and this as L, and this as x. So this equation actually has this kind of linear form, which is a Newton's law-based model of the car. So we can actually use this model in car tracking, and this is quite typical model in practice, also used in, for example, GPS. Another physical interesting example is the pendulum, which can be seen over here. So in the booklet you can find the equations for the movement of the pendulum when a white noise process is acting on the pendulum. So you get second order nonlinear stochastic differential equation, which then can be used for tracking the pendulum, for example. Yet another interesting example is mobile phone orientation tracking. So it turns out that actually the orientation of the mobile phone can be tracked using both gyroscope and the direction of the gravitation. So gravitation can be seen in accelerometers, which show upward acceleration of approximately magnitude 9.81. Of course, depending on the place where you are in on the Earth. So it turns out that you can actually write down the differential equation for the gravitation seen locally. It's a 3D vector, and the time derivative is completely determined by the local angular velocity measured by the gyroscope. So you will have a differential equation of this form. So this is the angular velocity cross product with the gravitation. So you can basically use, well, the gravitation is seen in different direction from the local perspective in the mobile phone when the phone rotates. But if you know the gyroscope measurement, you can basically calculate how it should move. But now the model is not perfect, so you typically want to add a white noise process here as well. So this is omega and this is a W. Now this models the orientation changes and also the uncertainties in the mobile phone orientation. And you can actually use this for tracking the orientation by postulating the measurement model. So you think that you actually measure using an accelerometer, you measure the local gravitation plus a noise process. So it's a 3D measurement and 3D noise. And then you absorb or actually model the linear accelerations in addition to the gravitation into this noise component. And now there exists a class of estimation algorithms called Kalman filters that can be used to track or estimate G trajectory from observations of Y in mean squared sense. So you can use Kalman filter together with this kind of dynamic model to track the orientation of the mobile phone.